A story from Italy in World War II. We've been sort of looking at questions regarding what had happened, and there's a little bit more of that, and then ultimately we get to the point of trying to tie in what happened to modern developments as far as pharmacology is concerned. So let me do a little bit more with this, sort of setting the stage. There's a lot of interesting sort of subplots involved with this that we'll see as we go through a little bit of the narrative here to start the afternoon. So remember that there's this fellow named Dr. Alexander who has been dispatched by the U.S. military to check into the possibility that there had been chemical warfare aspects of this situation that occurred at the Italian port of Bari, resulting in a huge tragedy. So let's see what observations he had as he began to explore this further. So it appeared to Alexander that sailors who had been thrown overboard and completely immersed in the harbor were burned extensively, while those in boats had comparatively superficial burns, wherever the toxic soup had hit them. Several men who had sat in this solution, possibly in lifeboats, had only local burns on their rear end and groin. A few lucky souls who took it upon themselves to wipe off the oily mixture that first night sustained only minor injuries. As he made his rounds, it was increasingly clear to Alexander that most of those patients had been exposed to a chemical agent. His sense of smell supported his hypothesis. Entering the hospital, he had noticed something different from the usual mix of sweat, urine, and disinfectant. Traces of an odor implanted in my mind said mustard gas, he later recalled. He knew that the three most common blistering agents were sulfur mustard, lewisite, and nitrogen mustard. And let me just do a little aside from that myself. We'll take a look at lewisite a little bit later when we do our little toxicology section to wrap up this semester. And lewisite is an example of an arsenic-containing chemical warfare agent, and it's a very interesting substance, and the treatment of it is very, very interesting. So that will tie in directly to us later this semester. Referring back to his narrative now, although generally referred to as gas, all three of these agents were liquids at room temperature, and all three produced skin injuries resembling burns and serious eye injuries. Particularly worrying was the new pure-grade nitrogen mustard developed by the Germans, which Alexander had studied the previous year. Here you go, Katie, at Edgewood, after 2 classified samples were smuggled out of Germany. Its effects were reportedly more rapid than sulfur mustard, and it could penetrate intact skin and cause systemic poisoning. Practically colorless and odorless, apart from a faint fishy smell, it was not easily detected in the field. It was also known that mixtures of these blistering agents in combination was a real possibility. It had been 5 days since the initial exposure, and if there was any chance of saving the hundreds of Allied sailors lying in hospitals all over Bari, plus countless Italian citizens, he would need to act swiftly. Here the plot sort of thickens. It gets pretty interesting here from another standpoint. He decided to put the question directly to the commanding officer, Colonel Wellington Laird. According to Alexander, talking to Laird, I feel these men have been exposed to mustard in some manner. Colonel, do you have any idea how this might have happened? None at all, came the commander's reply. As the chemical consultant to headquarters, Alexander was cleared to the highest degree. He knew the Allies had begun secretly stockpiling poison gas in the Mediterranean in case of an enemy attack. But he was skeptical that the Allies would have shipped mustard shells into a busy port like Bari and allowed the toxic cargo to sit there as a prime target for an enemy strike. Still, Alexander couldn't rule it out. Tactfully, he tried again. Have you checked with the port authorities, he asked Laird. Could the ships in the harbor have been carrying mustard? Laird replied, I have checked and they tell me there have been no such information available. So Alexander decides that he needs to sort of explore this on his own. So at first light, he headed for the harbor. He picked his way through mounds of rubble and surveyed the twisted skeletal remains of the Allied convoys. Out on the water, men were working like ants, removing jagged chunks of concrete and scrap metal. The port, which had been closed for 5 days and swept for mines, had partially reopened that morning. A number of burned out vessels had been towed out to sea. The dark, oil-slimed water in the harbor basin looked sinister. One sailor had recalled that the floating oil had been a foot thick on the surface of the water after the raid. It was a mixture of high-octane gasoline and fuel from 24 Allied ships, and Alexander suspected mustard gas or some derivative thereof, possibly dropped by incendiary bombs. Alexander wondered what other agents might have been thrown into the mix. It was known that phosphorus and magnesium bombs, which is, when you think about the chemical aspects of these, is a horrifying thought, both of which have caused deep chemical burns and eye injuries. Another possibility, and this is a scary one too, was that an Allied cargo ship had been carrying white phosphorus. Alexander found no evidence of mustard contamination in the survey of the dock area, and the Royal Navy personnel he interviewed appeared shocked at the suggestion that poison gas might have been released in the raid. Mustard, one British officer replied in surprise. That's impossible. There's no mustard here. So the authorities, the higher ups, keep categorically denying the fact that there could be chemical warfare agents around. Eventually, Alexander begins to dig deeper into this and begins to perform a series of autopsies. During autopsy, pathologists also found that the esophagus displayed a curious black longitudinal streaking. The lungs, a mottled blackish red color, were congested, the bronchi were filled with pus, and the trachea engorged with fluid. The stomach showed the same black areas, and there were necrotic areas near the opening, most likely caused by swallowing a diluted solution of mustard mixed with oil. We just touch more, and then I'll stop and we'll finish it off tomorrow. After studying the reports, Alexander concluded that many sailors who sustained blast injuries would not have succumbed to the hemorrhage were not for other complications. The serious consequences of imposing the mustard vapor injury upon a lung partially damaged or bruised by blast is at once apparent. Alexander was still trying to decide how to proceed, given the official resistance to his diagnosis, when he received stunning news. A diver he had ordered to search the harbor floor had found fractured gas shells. Tests performed on site found traces of mustard. Ordnance officers from the U.S. Army Air Corps identified the casings as belonging to a 100-pound mustard gas bomb. German mustard gas bombs were also marked with a distinctive yellow cross. This bomb was definitely American. So we'll see what he found out in addition to that, and then relate it to the realm of cancer chemotherapy as we finish this off at the beginning of class tomorrow. Okay, any questions or thoughts here as we proceed in our brief overview of membrane transporters and begin to transition our way into pharmacodynamics?
Keith, I just had a quick question.
Sure.
Yeah, so the membrane transporters and drug response, that is, you're presenting that from, I just want to make sure that it's open on Moodle for the students to be able to view.
Well, I put it on Moodle sort of right behind the drug metabolism
Okay.
PowerPoint.
Okay.
It's kind of a little bit up front in that regard.
Okay.
Now, hopefully I opened it up.
Okay, I just opened it up, and just the PowerPoint, and I don't think it's published to students right now, so I'll make sure that I just did it right now. So just want to make sure the students have that PowerPoint available if they're trying to follow along.
You bet. Thank you.
Yeah, no problem. I just wanted to make sure. Okay, great. Thank you, Megan, as well for the heads up. Okay,
Oh, you're welcome.
okay. Sorry.
No, not sorry at all. That's a good thing. Got to keep these things straight, and I certainly don't sometimes. So as we launched into this transporter PowerPoint, we're looking at some uh, essential, important aspects of known transporters. And bear in mind, my guess, I'm not, a super expert by any means at all in this field, but my guess is that there's going to be a lot more discovered about transporters during your lifetimes as pharmaceutical scientists. So this is just kind of the beginning, really. We see widespread application across the biological system. One of the aspects of pharmacokinetics, as well as ultimately important uh, processes which relate more to pharmacodynamics. So let's just look at some examples here. We won't take the time to go through all of them. At the lower part of this slide, which is actually labeled pharmacodynamics, this is where the field was starting off, again, to the best of my knowledge, a few decades back, um, as sort of I was getting to know pharmacology a little bit. So the neurotransmitter transporters, such as for serotonin and norepinephrine, were important pieces of information known in that era. And for example, as you can see over there on the lower uh, right side, the tricyclic antidepressants, which will still be part of our discussion on antidepressants when we get to it here in a few weeks, were thought to exert at least part of their mechanisms of action via the monoamine transporters, even at that time. And of course, at that time, the physical nature of the transporters had not really been isolated or identified. So it was studied pharmacologically, but the sort of detailed molecular biology that's known now was not something which was known at that time. Another really interesting aspect of this slide, I think, is sort of the mid slide there where it talks about proton pumps. And this has been an innovation in pharmacology, which was a revolutionary sort of one back a few decades ago. And of course, the proton pump inhibitors, which are mainstream treatments for gastric ulcer and related phenomena now, um, are even so far advanced that they're available over the counter. Um, I, I was amazed when I first encountered the proton pumps. I have a little bit of a problem with acid reflux, and a few about 2 decades ago now, just short of that, uh, my my mom passed away, and she had been using a proton pump inhibitor known as Protonix, and I did a no thing. I utilized some of her drug as we were clearing out her medicine cabinet in her bathroom, and so there was one tablet of Protonix left, and I had never tried a proton pump inhibitor before, and I took that one tablet, and my God, my acid reflux was just gone right away. It was just very rapidly and without taking anything else. And I was just stunned by how dramatically efficacious these proton pump inhibitors are. Um, so I think many of you are well aware of that. But the story gets more interesting, I guess, in the sense that at the time, 20 years ago, uh, the adversity aspects of the proton pump inhibitors was not as well known as it is today. And of course, these agents are still heavily utilized, but there's correlations with their use in some other undesirable pathological consequences, which has muddied the waters there in that area a little bit. So we'll see more of that again as we go along later in the semester. So there's a lot of different categories of transporters which are relevant as far as pharmacodynamics is concerned. And let's discuss this a little bit further as we go along. And of course, since the pharmacological and toxicological realms are so closely related to each other, no surprise that the channels and transporters and pumps and so on are relevant to our interest in adversity as well as efficacy, as we just talked about with respect to protonics. So the activity of these major macromolecular systems can be readily studied by standard biochemical means, and the results of those biochemical studies can be plotted out in terms of familiar saturation plots, hyperbolic in nature, much as what we see with standard dose response. And again, with the x-axis supplying the concentration or dosage, and then the rate of transport. Because these are enzymatic substances, many of them are anyway, not all of them, but many of them are enzymatic substances. You can plot the rate of transport. Of course, you can plot the rate of transport even if they're not enzyme related. But these plots should be familiar to you from your various studies of biochemistry in Michaelis-Menten kinetics of enzymology. And so because of the fact that many of these are enzymatic in their nature, you can do some of the manipulation of the data as you do with standard enzymology. And so you can, in sort of the good old days, these curvilinear plots were a little bit challenging to study quantitatively. In the era of computation, which we're so immersed in now, the computer can do a lot of that difficult mathematics for us. And so we see a lot of computer generated images in this regard in the present day. But one of the tricks that I'll call it a trick, but it's not really a trick, it's a nice tool that was typically utilized, and it still can be, but it's not so necessary now with computers, is to take a curvilinear plot, saturation plot like this, and convert it to a linear form. And you can do that with logarithmic techniques, or a very common way is to do a reciprocal or a double reciprocal plot. And you might remember the Lineweaver-Burke transformation of Michaelis-Menten curvilinear kinetics from your study of kinetics in biochemistry. So if you take this this curvilinear, hyperbolic curvilinear saturation plot and do a double inversion of it, in other words, do on the x-axis plot 1 over concentration, and on the y-axis plot 1 over the activity, you should come up with a straight line. Anyway, they're beautiful things when it really works out. And if you make your way around the halls of the Skaggs building and take a look at some of the posters from work like this, you'll see examples of these linearization techniques utilized to simplify the interpretation of the curvilinear relationship that's going on. So there are some various types of transport that have been identified. And I don't want to make a big deal out of this. Again, this is sort of transporter appreciation more than anything. But one of these subtypes is known as facilitated diffusion. And as you can see, this is a type of transport that does not require additional energy input because the transport's occurring down an electrochemical gradient. There are, specificity aspects in these relationships, as well as the ability to compete for the processes. And so in some cases, that's where a drug mechanism of action comes in terms of that competition process. Well, gated channels are ones that you're probably already familiar with from your studies in biochemistry and physiology. These are some of the first identified and most heavily studied of these various transport mechanisms. Uh, One thing that I'd like to draw a couple of things I'd like to draw your attention to. First of all, um, this slide, if you look down at the lower right-hand side, is from Ganong's physiology book, Review of Medical Physiology, which is, of course, one of the textbooks currently used in our physiology course. So once again, if some of these concepts are a little bit foreign to you or a little bit rusty in mind, since it's been a little bit of time has elapsed since we covered them, you could easily go to Access Pharmacy and take a quick look at Ganong, for example, to remember some of these matters. But the other thing I'd like to bring to your attention is the absolutely incredible activity of these channels. Look at that turnover rate. 10 to the 6th to 10 to the 8th molecular entities turned over per second. Boy, that is really moving along, isn't it? So that's impressive stuff, and puts it in there with some of the other enzymatic type of functions, which have such ability to perform so rapidly as that. Well, active transport requires energy input, and you can move substances against an electrochemical gradient, which is a really phenomenal thing when you think about it. These are subdivided into active transport 1 and 2, and personally, I'm not going to do a lot with that sort of designation myself. Maybe later on when Katie's talking about transport, maybe she'll go into that a little bit further. Right now, I'm just going to sort of breeze right on by. And this slide is sort of a typical slide you see in this area, in which the words that we've just encountered try to be represented in a schematic fashion with a figure like cartoonish like figure here. I'm not sure how well these cartoons work. They can be a little bit confusing, I think, also. But I would stick more with the words that we've already used in the descriptions on the slide, referring to downhill transport or uphill transport, as we just talked about in terms of opposing a gradient. If the cartoon works for you, great. If not, don't worry about it. At this stage, I'm not going to throw something like this onto the exam and say, please interpret this cartoon for us. These transport processes encountered in this slide, entitled vectorial transport, are really significant as far as the physiology is concerned of things like the gut, liver, and the kidneys. So it's just another category of important transporters. So we're sort of doing a potpourri of various types of transport as we quickly go through these slides. If the previous stuff isn't very familiar to you, perhaps this is. And I know I sort of probably do too much with sort of historical aspects of things, but it's a fault that I can't seem to get away from. And I will tell you that when I was in graduate school decades ago, the ABC transporters or major drug transporters were not known at the time, which is a little bit hard to appreciate now, since this is one of the most heavily studied areas currently, and certainly in the pharmacokinetics course, for those of you that are going to be involved with it, The ABC transporters are of immense importance there. It's very important in terms of the research that a number of people, including Erica, in our department do. So that's where I'm thinking possibly you've heard about the ABC uh, ATP binding cassette transporters, even if some of the previous types of transporters you aren't familiar with. So before long, if not already, you folks will know much more about the ABC transporters than I know. Just a few key things in this particular slide. Uh, First bullet point, ABC proteins are primary active transporters. They require ATP to actively pump substrates across membranes. Look at this there, and this number may be too low. Now, I'm not sure. Um, let me know if there's a larger number than this that's currently available from your studies in the pharmacokinetics course. But somewhere in the range of 50 known genes for ABC proteins that are grouped into a number of subclasses. One of the best examples of this is known as P-glycoprotein. And one of the first things I ever heard about the ABC transporters was with respect to P-glycoprotein. Also note that in terms of the actual connections to the practical world of pathology, that the cystic fibrosis transmembrane regulator is an example of a well-known and fairly extensively studied ABC transporter. So this is true pharmacokinetic stuff here, but the implications as far as pharmacodynamics are substantial because so many different drug substances are involved with the ABC transporter class of transporters. So this is just really more of the same stuff, although a little bit larger print. Uh, some important points we've already talked about the energetics of it a little bit. These pumps are mostly, but not completely, unidirectional. Many of these proteins move compounds from the cytoplasm to the outside of the cell, and that's a very important thing. For example, when you get to your studies of the pharmacology of cancer drugs, because in many cases, a prominent movement of anti-cancer agents into cells is countered by the opposite movement by the transporters pumping the substances back out. And that's a clear complication as far as cancer chemotherapy is concerned, in some cases anyway. So this so-called category of major drug transporters too, I think from my knowledge of it, is better known as the SLCs, or the solute carrier transporters. And this is another large family of transporters, very important with respect to the neurotransmitters, such as serotonin and dopamine, norepinephrine. So when we think about the transport phenomena that has been known for some time with respect to neurotransmission, this is a very central category as far as that is concerned. And just some little bit of detail about there are multiple subtypes of these SLC transporters, and this is just talking about that a little bit. Let me expand that a little bit as far as neurotransmitters are concerned. Not only were we talking about the pumping of neurotransmitters in a recycling sense back into the presynaptic side, but we're also talking about transport into membranous bound vesicles. So it's vesicular transport as well as plasma membrane transport that's involved in. As we launch into important nervous system categories with neurotransmitters being at the center of that, we'll be talking more about the SLC transport phenomena at that particular time. So this is just another um, accumulation slide of some of the terminology that we've been talking about here in the last few minutes, and see those things like P-glycoprotein and ABC showing up again. Do not need to memorize all of this at all. This is just trying to show you relevance. So the ABC transporters, of course, are not only important as far as physiology, but as far as pathophysiology is concerned. And indeed, one aspect of pathophysiology with respect to the nervous system has to do with those cases in which you're utilizing a transporter inhibitor, such as an antidepressant drug, to try to reestablish uh, homeostasis with respect to the transporter function. Now, as we'll see when we get to antidepressant drugs, there may be mechanisms that go well beyond the transporter realm, but certainly for a very long time, the central nature of transport pathophysiology and treatment of that has been crucial in a number of central nervous system disorders. And again, you do not need to memorize all this at this point, but just giving you some examples of important therapeutics relative to P-glycoprotein. Same sort of thing here. Just trying to make this relevant. Pharmacology is both a basic science and an applied science. And as we move through our studies of pharmacology here, we'll be moving from the basic science realm more and more toward the practical applied um, therapeutic realm, and tying those things together. And for those of you that are ultimately going to be practicing clinicians, the relationship of these basic concepts ultimately to the applied realm is, of course, the most important thing on your minds. Is quite reasonable for you to be that way. So this is just, on and on examples of it. It's an extraordinarily important realm. There at the upper left-hand side, you'll see glutamate. Glutamate is a neurotransmitter that we haven't talked about much now. I've talked more about the classical biogenic amines, but glutamate has forged to the front in the last few decades as being a critical neurotransmitter, as well as, of course, an important ingredient in the amino acid soup for making uh, proteins. But our particular interests are more in the realm of glutamate as a neurotransmitter, and you can see some examples of that listed on the right side of that box in terms of Lou Gehrig's disease, for example, potentially Alzheimer's and other neurodegenerative disorders, and to some degree, even disorders like depression, which have been looked at in sort of different light than this previously, but now looking further into mechanisms of action and potential applications therapeutically. Neurotransmitters like glutamate are playing a big role there. Well, this is just sort of overkill. Again, this is too small to even read, but it's just, many more applications of transporter phenomena as far as physiology, pathophysiology, and ultimately therapeutics is concerned. Same thing, although here very, very heavily beyond the neurotransmitter realm into the realm of hormones, which you and I will be together with in our very last topic that we cover spring semester. And some of the vitamins, some of the vitamins of which are, of course, very similar to hormonal substances in their own right. So this is just sort of saying some of the things that I've been talking about along the way, the importance of these transport phenomena as far as central nervous system pharmacology is concerned. For the time being, just put it in your back pocket and say, here's relevance. We're going to be using this as a tool as we study central nervous system pharmacology in upcoming weeks. So we've got a little bit of time left here. Let me just make a quick movement into our realm of pharmacodynamics. So let me start here. So all along so far, we've been pointing the life history of a drug substance as far as pharmacokinetics is concerned, the drug entry into the system, its ultimate exit from the system. In that intermediate phase of life history of the drug, at certain time or times, the drug is going to be at a concentration which is relevant to the particular dose response for that particular drug, and that leads us to drug effects, or also known as the science of pharmacodynamics. Before we introduce that a little bit more, just some an interesting bird called burrowing owls that I wasn't familiar with until till I saw this slide one time. But maybe that is a stress reducer for you. If not, there's hip shot again. Here's an interesting story that I'll tell you the major story. Either Katie or I will when we're talking about opioids later in the semester. But this cat is named Bob, and he's the buddy of this guy named James. And this is a street scene in London. James is a street musician. And as it turns out, the relevance to us is he's a heroin addict. And there's a really incredibly neat video of the relationship between Bob and James with quite a bit of insight with respect to addiction and dependency. So if you go to, I believe, one of the online sources, such as YouTube, and just type in there a cat named Bob, I think you can find that video. Anyway, more on this as we move later in the semester. Well, we've already talked about, what is a drug and controversies associated with that. That we are heading into an era of rational use of drugs, which hopefully will develop new agents which have greater efficacy and lower toxicity. We've, in an association with that idea, talked about the idea that drugs have multiple dose response curves leading to multiple effects. Some of these we typically characterize as beneficial effects. Some of them we characterize as detrimental. The relationship between those good and bad things is what we call risk-benefit analysis. And really for the remainder of the course, and really the remainder of your careers as pharmaceutical scientists, you'll be weighing these various risk-benefit phenomena against each other as you decide in how much role a particular drug substance or substances are going to play in the therapeutic realm for your patients. Other general principles that we've already talked about a little bit as we were introducing things a couple weeks ago, we talked about state dependency and how that has become such a burgeoning area of study. And of course, the ever impressive idea of dose response. And at least for my purposes, if there was just one question on any pharmacology exam, what would it be? And that would be name the most central of all pharmacodynamic effects, and that is dose response. Drug effects in our way of looking at drugs are dose dependent. Not everybody in the world looks at drugs in that particular sense. So dose dependent phenomena is a characteristic of chemically, biologically based pharmacology, which I'm trying to hit some of the high points with you on. You may well be familiar with other realms which utilize drug principles which do not go by the great importance of dose responsiveness. as I'm talking about here. So that's just a little sidebar comment on my part. Well, as the last 100 years have unfolded, the idea of a drug receptor has become reality in terms of the experimental research that goes into this particular area. Many, but not all, so-called receptor substances for drugs are proteins uh, in their nature, but there are other drugs targets than that, and the idea of a drug receptor requires really two ideas, and that is that a receptor must be something that binds a protein, uh, often with very high affinity, although not always, and that binding phenomena is linked to some uh, aspect of modulation of cellular function via an endogenous effector or effectors. Many receptors, but again, not all, are on the cell surface or close to the cell surface. Uh, Exceptions would be the steroid receptors from that whole class of nuclear receptors. Those substances penetrate the cell and encounter a receptor internally, either in the cytoplasm or in the nucleus itself. But huge numbers of receptors are either surface bound or very close to the surface bound. And of course, the huge category of G protein coupled receptors are an example of that. Um, if you recall, the receptors there are not always necessarily on the cell surface per se, but sometimes are just a little bit buried into the cellular membrane about a third of the way in. And we'll talk more about that as we review some aspects of the G protein coupled receptors here in the upcoming day or two. So the cartoon here is a little bit too rigid for the way the biology really exists, but this relates to the initial way from enzymology that researchers in the field talked about a lock and a key, and the receptor or the enzyme in those particular cases was the lock, and the drug or neurotransmitter was the key, and the insertion of the key into the lock opened the lock up. It's not a bad analogy. It's just that in terms of additional studies that have been done with relationships like this over the last few decades, recognize that the drug and the receptor are a little bit more malleable than just a key and a lock, and we'll talk about those differences as we proceed here over mostly tomorrow. We should pretty much wrap this up tomorrow, I think. So if you think back to biochemistry and Michaelis-Menten enzymology and the relationships that existed there, the most straightforward aspects of drug receptor interactions are very, very similar to Michaelis-Menten enzymology. And of course, some drug receptors are enzymes, and so there the analogy is really tight, but it really goes beyond that. So as we pick up on this tomorrow, we'll talk about the relationships between drug receptor binding and substrate enzyme binding in enzymology, and this is where we'll start. So I don't know if anybody has any questions that we can approach here at the end of the hour today. We can go with that. Otherwise, we're done for the day, and we will rendezvous once again at 1 o'clock tomorrow for a look at some of these pharmacodynamic phenomena. Thanks much, everybody. Have a good evening. See you tomorrow at 1 o'clock.